streaming. Good. So that shouldn't mean the video. Okay. Now we hit start streaming. Make sure you want to start streaming it. Okay, we should be live. We are streaming now live, everyone, and I think we're muted. So, with us being live right here, what questions are there? And I think people here in class want me to go through everything. How many people do we have live online now? We have 2. Started with 2 last time, we got up to 10, so we'll beat that out. So hopefully I changed the delay and the video looks to be a little bit better. A little choppy, but the audio is good, and then I make the text as big as can be, and I think they can actually see the text better this time while it's live. So let's go through chapter by chapter, is one of the things they were saying in class they want to do here. So I'm going to keep this review sheet up. Let's start out with the first chapter, and there's our spinning wheel of death. So pretty on the Macs, right? This is what happens when you run everything on a little tiny MacBook Air. It's fine, it'll get over it, or at least it used to. But the first chapter we're going to talk about right here is the chapter on the test, which will be testing proportions. So what we're mainly going to try to do right here, and online, feel free to ask those questions if you have it. I can see everything. Hey, Chelsea. We've got 4 people watching now. And is the stream quality better now, Chelsea? I think the visuals should be better. And you will be lagging a little further behind right now. Still ask those questions online. But I think online will have better quality now because I made it longer lag. So it has more time to ingest the video and take it down or take it in. So we're going to go chapter by chapter. And let's start with the very first chapter we have for this test, which is testing proportions. That, I think it's chapter 15. I think it is. It's weird, because then we go to chapter 14, right? We go back. They changed the book recently and changed which chapters the ordering is, so that's why it got a little bit different. But with testing proportions, we need to start, and let's do some conditions to start. So I always like doing conditions because it's very good practice. They can be on the test, and I consider them easy points. So every time we do a chapter, we're going to go through them, spend about 30 minutes on each chapter. Does that sound good? And if you have to leave, this will be posted, so you can come back and be like, hey, which chapter when? We'll try to put the timestamps in the video so you can be like, hey, let's go to this chapter. Let's go to this chapter. So the first thing we do here is conditions. So conditions for this chapter. The conditions for the chapter. Now my class knows this. Condition 1, random means we took a random sample. And you can call it, I think in the book it might call it randomization or random sample. So we can call it random sample condition, randomization. I will just call it random. It's the random sample condition. Did you take a random sample? And we only violated this one time on a test a long time ago because students got so used to being, yes, it's a random sample. But when you get to a test question, what should you look for in that test question? Right here. That right there is your key, that it's a random sample, especially when it comes to art questions. When you get to a test question to check to see if it's a random sample, we just try to tell you it's a random sample. So we try to make that as clear as possible, pretty easy, because in truth, in the world, it's a lot harder to take a random sample than just saying you did. Don't worry about going too particular on it. Just if we don't say that it's a random sample, don't say it's a random sample. We're going to try to make it as clear as possible on the test and not try to trick you, though. So that's condition 1. So, and there are no numbers to these conditions. But why do I like to do condition 1 and then condition 2? Because they're always the same, at least for this test, this chapter. We did learn conditions a while ago, like quantitative variables, straight enough, no outliers, as my class knows, QQ, straight enough, no outliers, plot doesn't thicken. But those conditions are for different types of tests and for different things we're doing. So, oh, nice. Thank you, Chelsea. I'm glad it looks way better. I've changed the stream settings. That way we're on a longer lag, and I can see it looks better too. Awesome. And also the video we recorded earlier looks great too. So the second condition, and this is only for this test for these chapters, the second condition is the what condition? 10% condition. This one's a weird one. We can talk about it a little bit here. We might not talk about it every single time. But the 10% condition states that we must do what? Exactly. So the 10% condition, and so sample less than 10% of the population. And we put this in our last video. We actually violated it. So we violated this in our last time that we were here because in this problem, we sampled 200 Stat 201 students. These were Stat 201 students. I should put 201 students at that, so let's write that right here. 201 students, Stat 201 students. We went out and spoke to 200 random Stat 201 students, but how many students take Stat 201 a semester? About how many did we say? About 1,000. Now I know this problem doesn't tell you all that info, so don't worry. What if it was UT students though? Would that violate the condition? No. So the way you look at this is you say, there are 200 students in my sample. Stat 201 has 1,000. So that is 20%. Can everyone do 200 over 1,000? And double check if you want, but that will be 20%. But if you had all of UT students, let's say there's 20,000 UT students, then 20,000, 200 would be what percent of that? 200 out of 20,000 would be, it would be less than 10%, it would be 1%. Does everyone see that? So there's a lot of ways to ask this, like we sampled adults and asked who they're voting for. We spoke to 1,000 adults in the United States. Do you think that's less than 10% of the US population? Yeah, and saying something like 1,000 US adults is definitely less than 10% of all US adults. That's probably good enough for anybody right there to think it. If you said something about UT, you might say, given UT has at least 1,000, we sampled 200, right? Given UT has at least 2,000 students, which I assume it does, 200 is less than 10%. So if you notice what this condition is, very important, less than 10%. And I know that's counterintuitive. It goes into a little bit of mathematics and how the error gets worse, but it is less than 10%. So I'll kind of, rather than going into a big lecture and why is it less than 10% and showing all the math theorems, will you guys accept with me it's less than 10%? No, don't worry. It's from my first semester teaching to now, and it's not a bad question. Why is it less than? I thought more is better. It relates to the error and how error is created in finite populations. So that is why. And then the math is the extended reason, which I won't get into. And I just hit enter in a spot where I wasn't at. So let's continue back down to here. We misspelled sample. Now here's where we have to pause. And why do I always say pause when you get to condition 3? It depends on the variable. And this is something we were talking about earlier. We were talking earlier about the different types of variables we have in the notation. So you'll notice here we have categorical notation, quantitative notation, and we also did some chi-squared notation. So this is really good for your formula sheet. This will be posted just so you can make sure you know what every single thing is. And I don't think we have the formula sheet up right now, but we can look at every single thing in the formula sheet, which we're going back to really bad internet again. And so we'll check out that formula sheet again later. But it is in the last video when we went through it. So if you want to review the notation, it's all there for you. So when we get to condition 3, for this, remember we're testing proportions. What will be the third condition? Success, failure. And the success failure condition is we must have at least 10 successes and 10 failures. We must have at least 10 successes and at least 10 failures. And this can be done via a few different formulas. The formula we would use for a test is NP naught, NQ naught. The formula we'd use for a confidence interval, which is from the last test, is NP hat, NQ hat. The formula we'd use for sampling distributions is NP, NQ. Now what do you notice is the difference? It's always got N, and then it's got some from a P and Q. Now when we do this on our test, which I'll write a test question here in a moment, and we'll go through the steps on this, we're going to use the null proportion. So when you're hearing me saying all those things a moment ago, you can see we have all of our cheat sheet here for the null proportion the true proportion, the sample proportion, all of these things. We'll look at the formulas, but make sure you kind of know this, because this chapter right here, be writing these down if you need any of it, or take a screenshot if you want and reference it. But right here, this is what we're going to be using to do these problems. We need to make sure we can say all of these when we read through a problem. So let's go ahead and try to do a problem now where we're going to see the notation and we're going to test a proportion. So let's go ahead and write our problem. I usually write some pretty simple problems when I'm writing these. You know, a lot of problems like to give you a background, like the University of Tennessee is very interested in whether or not students are going to the new Starbucks. They would like to know that at least 10% of students go to Starbucks, the new Starbucks. So let's write this in here. Let's destroy some of that background. Do more than 10% of students go to the new Starbucks at least once in a semester? We went out and spoke to how many students? 100, nice number, right? 100 students. And, can't see what I'm typing. From this 100, from this sample, how many? Careful. Ooh, we're going to get an interesting... Wow. Let's do that. Let's use 47. 47 of them said they go to Starbucks. Run. I knew I misspelled that there. What I'm actually going to do, since Mubarak chose 100 students, I'm actually going to change. I'm going to change this to 200 because I don't want us to be on the edge of violating a condition. Do you see it? Yeah. With 100, the NP naught, NQ naught condition would be 10 and 190, right? Or 10 and 90, I meant to say. I've already doing the other in my head. It'll be 20 and 180 now. So let's go ahead. What should I include in this question to make it? We went out and spoke to 200 random students. So we're going to try to add that keyword in there to make sure we know we meet condition 1, random. And why is it random? So probably on your test, I'd circle that. If you see me highlighting stuff, it's where I suggest you circle it. Circle that on your test. Boom, condition 1 is met. It's random. Condition 2, 10%. I want you to try writing a sentence right now. I want to see you write that sentence online too if you can. Write me a sentence right now that you would write on the test on whether or not the 10% condition is met. And take a moment. Write that sentence. So just take a good 20 seconds. Shouldn't take that long to write it. Pretend you're at the test right now and write that sentence as though you're at the test. What would you write?
200 is less than 200 is less than 10%.
I like 200 students is less than 10% of all UT students. Yeah, throw in a little context there. You're probably all right if you do that. The graders are a little bit nice on this, I do agree. But 200 is less than 200 students is less than 10% of all UT students. It seems reasonable. I mean, you told me 5,000 is less than 10% of all UT students. I'd be like, are you sure 5,000 is less than 10%? That doesn't sound like it, right? But 200 is less than 10% of all UT students. Sounds very, very reasonable. And writing this out, practicing it, is a good way to make sure you have it down. Success, failure, and we did slightly change the question because we wanted to make sure we passed it. And I will tell you this much, on the test, we won't give you exactly 10. We won't play, wait a minute, it's exactly 10%, or it's exactly 10 successes and 10 failures. Because even then it's like, well, it's funny, I was reading an article, and it's like, some statisticians use a 5% condition. I was like, well, because why 10%? Why not 5%? And then success, failure, there's all this iffiness. It's like, well, when is it actually good? So we're going to use these numbers here, but we're going to make sure we meet the condition. And to check the last condition, I'm actually going to put it right here. Let's go ahead and solve the last condition mathematically. To solve the last condition mathematically, we're going to do NP naught. And the reason we're doing P naught is because we're testing a proportion. And NP naught needs to be what? Greater than, I hope that's not lightning. And this will equal, what formula will this equal? NP naught equals, tell me mathematically, what is N? 200 times 10%, right? And then, whoops, got my star between that. 200 times 10%. Does everyone see how I'm finding these? Does everyone see what I have right here? 200 times 10%. Now be careful, you see the 47 in there. Maybe we'll mark some notation here in a moment. That 47 is not P naught. We'll use it for something else in a moment. But we need to see that we have at least 10 successes. And what we see right here is how many expected successes do we have? According to the null, we have 20. And then you should be able to tell, because when you do NP naught and NQ naught, NP naught and NQ naught, what will they solve out together when you do NP naught and NQ naught? They will solve out together for what when you add NP naught and NQ naught together? They'll solve out to what? Nope. 200. P naught and Q naught add together to 1. Remember your P naught and Q naught game. If P naught is 0.1, Q naught is 0.9. If P naught is 0.4, Q naught is 0.6. They're just complements of each other. They add up to 1. But then when we do NP naught and Q naught, that's where we have the two added together equal up to N. Because you're basically saying, if I expect there to be 10% of people who don't go to Starbucks, then I would expect out of 200, I'd expect 20, which is 10%. Does that make sense? According to the null, I'd expect 20 people out of 200. And then how many people would you expect not to go to Starbucks? 90%, which is 180. And then we know we passed this condition, and we showed it mathematically by showing there's at least 10 successes and at least 10 failures according to NP naught and NQ naught. And you notice I'm using P naught because this is running a statistical test. And it'll actually go into one of our first conditions right here. Let's write out the general form for this right here. We're going to write the general form of our null and our alternative. And I'm going to cheat because we did a null and alternative up here, but watch out. So I'm just going to steal this for the moment. But it won't be this. Why is this wrong right here? And why on the test would you be like, if you're hearing students who go to Starbucks, why would this be wrong right now? Because this is proportions, and that right there is means. When you hear if students go to Starbucks, that should be proportions. And I guess technically it should be capital P. So right there we have the true proportion is equal to some hypothesized proportion. Does that make sense? Just reading it as is. But I always want you, and I beg of you, if you remember back to your project, remember when it said write it in statistical notation and then write it as a sentence. You remember that on the project? That's where we need to practice reading it ourselves. Right now, reading this, and I'm going to highlight it as I read it, it says, the null states that the true proportion is equal to some hypothesized proportion. So wait, what did we hypothesize up here? We hypothesized what was true. Does that make sense to everybody? That is what we hypothesized. So you should mark right here that this, make sure you know this, is equal to what? That is equal to 10%, but in notation, what was here just a moment ago? The hypothesized proportion, P naught. Just a moment ago, we'll go back in time here. Just a moment ago, P naught was there. So P naught is 10%. Does that make sense? So we just have to make sure we note everything. Be like, that's my null proportion. So 10% is the hypothesized amount. And I also, I see another thing in that first sentence. What is this going to tell me? So what? And writing the alternative, here's the easy part. If you write your null and you get it correct, is it pretty easy to write the alternative? Yes, because what's the only thing when you do statistical notation that will change about the alternative? The sign. And I should put a what here? Greater than. And now read it as a sentence. Read all of this. And I'm going to highlight it as I read it. The null states that the true proportion of students who go to Starbucks is equal to 10%. We're talking about like a specific Starbucks. The alternative states that the true proportion of students who go to Starbucks is greater than 10%. And that's exactly what we're doing right here. And also, I want you to note something. The way I'm reading these nulls and alternative is really going to help at the end when I say some very simple things like I reject or I fail to reject. And we'll talk about that when we get to it. So what we have here is we have a few other things to note. Right here we have 200. What's that going to be? Random sample, that's going to be n, sample size. And then this one is the one people always forget. X, nice. Now we're not forgetting it. And if you want, make sure to review the notation that we have right here where we go through and mark everything. Sample size is n, 200 students were sampled. 47 is how many students went to Starbucks, number of successes. P naught is what we hypothesized to be true, 10% at the start of it. Question? Sure, let's just take some quick notes on that and make sure we have it in notation. Yeah, so we have here n equals, and it's lowercase n. It always tries to capitalize it on me. It's like, I'll be helpful, and it's like, you're not being helpful to it. X equals, is going to capitalize that, nope. 47, P naught. So do P naught, I think that's it. Oh, we have them up here at the start, and so they're at the very start of this document, and I'll upload the document. And it's at the start of the last video. So we, does that make sense? And do you wanna go right here? Are you talking about these symbols?
I think it's like explaining like
The null.
Oh, okay, the null. Wait, this right here?
like say
Oh, right. Oh, right. Okay, write that. Thank you, guys. This is your guys' review. So you're saying the null states that the true proportion of people who go to Starbucks is equal to 10%. Is that what you guys wanted right there?
Yeah.
The null states that the true proportion of people who go to Starbucks is equal to 10%. So that's what we have right there. And then the alternative states that the true proportion of people who go to Starbucks is greater than. Try to read each part of it as a sentence. This just says, what is this part of the sentence right here? The null states that and then this right here is what? The true proportion of people who go to Starbucks, and then this right here is, and then is equal to 10%. And just try to do it as a sentence. Try to read through it bit by bit.
If it had said, wanted to know if students go to Starbucks, just if they do or don't, the alternative wouldn't be greater than, it would be not equal to.
If it said, correct. If it said, do 10% of students go to Starbucks, then it would just be not equal to. If it gave no preference. And the reason we did greater than, you are correct, is because my question asked, do more than 10% of the students go to the new Starbucks? So, question, great job.
if we were to put 0.10 instead of 10%.
Sorry, Wes. It looks the video is super frozen behind. Go ahead and ask again. I'm sorry.
If we put 0.10 in the sentence, would that still be kind right instead of the percentage?
Correct. You should be all right. I usually just change it to a percentage, or you could say proportion. Proportion and percentages are pretty interchangeable, and so you could do 10%. I would probably do 10%, but you should be all right if you put 0.10. They're interchangeable as is. So the video might be best, for those watching online, the video might be best after it's uploaded. Down here in the pit, as you guys know, I've done live broadcasts. I was just telling people about how we broadcast via YouTube, and they're like, oh, that's so cool. And I'm like, oh gosh, I hope they don't watch this live broadcast. They'll be like, whoa, it's choppy, it's frozen, it's so far behind. But the video recording, I am choppy in the video recording, me, but the quality of video and the quality of audio is there. So if you go back and review this, you'll be able to see all the example problems, and we're working through them step by step as though it's a test problem. So it's my best thing I can do right here to mimic test problems and kind of practice and get the notation down. So we have right here P naught, and Q naught is just the complement of that. Let's go ahead and write our formula. So we're going to try to write the formula by scratch. Every time we do a statistical test, we'll always solve for a what? Think it's a two-word thing. Every time we do a statistical test, we'll always solve for a test statistic. In this instance, we're going to solve for Z, I say this, I'm sure Mr. T is a very nice guy, but I always say Mr. T is mean, because when we do means, we use T. So I haven't been saying it much this semester, I don't think, but I usually say it. So I'm getting the formula set up here for the z. I just have to put a radical on this. Yep, that's correct. And then let's go ahead and write in here. We need to take P naught. Well, let me toss this in. I will just add it in. So we need to do, let me just think, P hat minus P naught. Good. So let's insert. The top part of every statistical test that we do is always a what? The top part of every statistical test is always a what? Think, I'm subtracting two numbers. I'm subtracting two numbers, it's just a what? A difference. And then you take that difference and you what that difference on the bottom. The bottom of it, say it again, Mohammed. I thought Mubarak. Mohammed. There you go. I didn't know who said it. You take that difference and you what it? Standardize it. So here is the formula you would see on the formula sheet. And if you look, it's just a difference standardized. Does that make sense? The bottom of this is the standard deviation. It's often called standard error, but in this one kind of rare instance, at least with testing, this is a standard deviation because it's based on what we believe is true. So we have here our formula. Does that make sense? We're going to take the difference, and what you might notice is that we need something that we don't have right now. What do I not have notation-wise? I don't have p hat. How will I solve for p hat? Correct. P hat equals to, it doesn't equal to v. P hat equals x over n. Wrong button. Oh, what was the question? Oh, awesome. Thank you very much. P hat equals x over n. So we should, I'll try to do it in my head if you guys want to tell me if I'm right, it should be 23.5 or 0.235? 0.235, good stuff. So let's put over here x over n, and we're trying to write everything out so people can see it nice and clean on here, nice and big. And this equals to, the hardest thing is the lag in the video. I have to like look back and forth because I have to look at this screen to see what's happening. 47 over 200. And then we're going to have here 0.235. So that right there is p hat. So we just take p hat right here. And I want you to think about this. Just think about this logically. Don't use statistics yet. If I were to tell you we went out and spoke to 200 students and nearly a what of them? That's nearly what of them? 23.5 is nearly what of just kind of a general, like nearly blank amount of our students went to Starbucks. Nearly a what? 25%. Nearly a quarter, right? So nearly a quarter of the students went to Starbucks. Just think, is that a lot more than 10%? Yes. Now don't reject the null because of that. You might think it's good evidence, though, just kind of what we know. It's like, imagine if we saw 90% of students going to Starbucks. Well, of course, everyone's going to Starbucks. It's Starbucks. But this seems kind of larger than 10% with what we know. So do you think the z-score will be kind of large or very small? Larger. What is the smallest z-score could be in terms of absolute value? The smallest z-score could be is what? Say it again. 0, right? Because when would we get a z-score of 0? If in our sample we saw what? We'd get a z-score of 0 if in our sample we saw a sample proportion of, because then what does the top of that equal? 0. And then if you saw 10% and you expected 10%, wouldn't you continue to believe 10%? Because that's what you're like, well, I think it's 10%, and 10% of students in my sample went. Well, it looks like it's 10%. But remember, we could get differences that are small. And I'm not saying this is not our problem, but think about that. The top of that's only a difference of 0.01, which seems small. But we always have to standardize the difference to figure out if it's large, right? And this would be a different problem right here. I'm just showing some examples where in this instance, the z statistic would probably be smaller, and we'll see what would happen because maybe we'll do another problem with this. But let's go right here. I cannot believe it. It's almost been like an hour. Now here's the problem. What numbers am I going to put on the bottom? A lot of people make mistakes on this. Correct, because that's p naught and Q naught. Be careful. A lot of people accidentally put P hat down here, and that makes a mistake. Then I'm going to try to solve this in my head again. I was able to do the last one. Okay, don't tell me the answer. Well, oh, that's going to be fractions. Oh, no, that's no fun. That's 0.005 square root. I don't know if I can do this one in my head. I'm taking a guess at it. Wait, I'm going to get close. So go ahead and solve this in your calculator. I'm purposely leaving a lot of these up, asking you to solve it in your calculator to see if you get the right answer. And we'll see if we all get the right answer here. So give me a second. I'm trying my best to do it in my head. You got it already? I'm thinking, is the z-score like 3-ish? What's the z-score?
6.36.
Ooh. Yeah, this was harder. Fractions in my head. 6.36. 6.36. So that is the z-score. This means, see James? This means that we are this many standard deviations above the mean. To put this in context, this would be like meeting a guy who is about 7'10". Is that unusual? Is it like a little unusual? You're like 7'10", No. That's like crazy unusual. Because things that are unusual are how many z-scores away? 3. Like 3 is a pretty big z-score. This is double that. Like 3 in terms of heights would be someone who's like 6'4", 6'5". That's pretty unusual, right? Like Mohammed, you're 6'5". Are you pretty tall? Are you the tallest person out there? No, but you're very tall. But when someone's like 7'10", you're like, whoa. That's like, whoa. So this is extremely unusual. And I keep talking about how unusual this is because we've just done our second to last step here. I should say we're about to do our second to last step. Once we get this z-score, which is 6.36, we take our z-score and get our what? We take our z-score and get our, from the z-score, we will get the, no. Z's and T's don't go together. If you're using the z, you're not using the t, you're not using the chi-squared. From the z-score, we will get the, you're getting closer. Think, I kept telling you how unlikely this is. The probability of our results or results more extreme happening by random chance variation, given that the null is true, is a p-value. Exactly right. The p-value is the probability of our results. And we kept saying how unlikely or rare this is. Now, you could on the test say something like, what we observed has a z-score that is greater than 3. Does that sound very unlikely? Yes, and when we say 3, you can say an absolute value of 3, because negative 3 would be very unlikely too. That'd be like, if you think about someone who is 4'6", that's very unlikely too, right? It's like nothing wrong with being very tall or very short, but they're just unlikely heights that we don't see very often. They're on the farther ends of the curve right here. The most common heights, like if you see someone and they're 5'8", what do you think? You're like, oh, I see that all the time. And then you see someone 7'10", you're like, whoa. You're like, that is very on the far end of the spectrum of what we see on the distribution of heights. So we have unusually low, unusually high, and we know if something's unusual based on its what? Its z-score, and then from the z-score we can get the p-value. That's exactly, from the z-score we can get the p-value, which tells us the probability. If it's unusual, the p-value will be closer to 0. And now remember, let's look at our test. This is key for getting the p-value. What is this that I'm hovering over now going to do for our p-value when we get it? What does that tell us right there? When we go to our curve, that tells us which way we are going to shade the curve. We are going to shade above 6.36. So all I do is I go here and go to above and go to 6.36, and what do you guys think the p-value will be?
9.8.
You've got all the decimals, and it's basically 0. So it's basically 0, and you can do this on the calculator. Maybe we'll mention briefly, this is one prop z-test on the TI calculator. If you have your TI calculator and want to do this problem instantaneously, go to stat, and then test, and one prop z-test. Stat, test, one prop z-test. And do you guys see it? Stat, test, one prop z-test. I do not... I'm getting scared when the screen is shaking. I think it's Volapalooza above us. So stat, test, one prop z-test. Stat, test, one prop z-test. Hopefully the stage is, no, stage shouldn't be above us. Stage is over there. I don't know what they're doing. Stat, test, one prop z-test. And I believe is that exactly what it says on most of the TIs? And you should see X, you should see N, and you should see C level. Now, please, 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 if you think you might use your calculator on the test, practice using it. Don't walk in that day and be like, I'm just going to use the calculator, I got all this. No, no, no. It'll be confusing. You won't know what to click. You won't know what the output says. Try doing this problem with the calculator, then try doing it by hand. If you can do it on the calculator, if you can do it by hand, you have a double check. I always teach it just as a backup. So what do we have right here? We have our p-value is basically 0, and we're seeing that right here on this graphic. Pretty easy to see that 0, it would be 6 would be way over here, 6.36, and it just shades to the right of that. If the z-score had been 2, then we would have gotten this. We're going to play a fun game here, Mubarak. So if, I think I can do this right here. Okay, what if we had 24 people? If we change this to 24, we're just changing the problem to 24, right? So 24 would be what percent right here? 24 out of 200 would be what percent? 12%. Does that make sense? I'm changing the problem. And you should be able to change it like this on your calculator. I'm going to guess the z-score now because I've gotten a good bit of info. So I'm guessing that the z-score now, is it 1 point something? Is it 0. Oh, come on. It was basically 1.0. 0.94. I was going to guess like 1.1. It's not 10. But now you'll notice, here's a problem we run into on the test, and I've changed this problem drastically now to what now this problem is going to have a higher p-value. I'm going to get to that p-value almost decimal place accurate. You ready? The p-value now is 0.3. Oh, no, wait. Did you guys do the right test? Oh, no. Why am I saying that? 0.17. Oh, yeah. I know what I did wrong. Let's go ahead and look at this right here. Because if you look at what we have right here, it's to the right. And what is outside of one positive and negative z-score? First z-score has, inside of it has 68. What's total outside? 32. What's one of my hands worth? 16. So I kind of thought it through in my head. I realized when I gave you 32, 33, I didn't do the one side. I was trying to do it a little bit quick. Now, you won't have to do that on the test, but it makes sense to me logically why this is here. Now, I wanted to change the problem for this reason. The reason I changed the problem is I changed the problem from rejecting the null to what? Failing to reject. Now, if you look at the p-value now, we say the following saying in my class. When the p-value is low, reject the null. When the p-value is high, just let it fly. Just let it be, which means what? It means we fail to reject it. Does that make sense? When the p-value is low, reject the null. When the p-value is high, just let it fly. Just let it be. And you're right. And as Mohammed said right there, let's go back to what we originally did, because we're on the final part now. We've got our p-value. So if you think of all the steps we did our conditions, step 1. Next thing we did was we did the mathematics. After doing the mathematics, we found the p-value, and now we're going to state our conclusions. So these are really the steps we'll go through when we do another statistical test here on another chapter. So now we need to state our conclusion. But if you've done this, if you were able to read this at the start, stating your conclusion will be just as easy. And we have changed this now. And I'm going to change this from right here, and say, I fail to reject. And I guess I need the. I fail to reject the null. I'm going to put states out. I fail to reject the null that the true proportion of people who go to Starbucks is equal to 10%. And if you fail to reject, do you have evidence for the alternative? Correct. You do not have evidence for the alternative. And that's sometimes why I like to say do not reject. Sometimes say I do not reject. I do not have evidence for the alternative. But if I do reject, I do have evidence for the alternative. I like to, sometimes I say it that way. I do not reject the null. I do not have evidence for the alternative. I do reject the null. I do have evidence for the alternative. And do not reject is the same thing as fail to reject. Question?
It seems like when it says like I fail to reject, it feels like a double negative.
It's so crazy. So the reason we usually say fail to reject, it means the same thing as continue to believe. So I like do not reject, just it makes more sense like the way we speak these days. It's just the way people originally wrote this in statistics. They always say, I fail to reject. And I think maybe they thought they're being so haughty. But if you go into a boardroom and they're like, we failed to reject this, it might make more sense to say, we think this could still be true. And that's what we're saying right here with this one is saying, we thought 10% was true to start, right? So you see where our initial belief was 10%. And then we did see something higher. I did change the question. So I changed just the statistics right here. I changed x to 24, which makes this, I should change this also. So that changes this right here. I just wanted to make it different. But even though I saw something higher than 12%, higher than 10%, was that enough evidence? No. Because I saw something higher than this doesn't mean it is higher. Like imagine your friend said to you, I can run a mile on average faster than 6 minutes. So you need evidence that their true mile time is less than 6 minutes, right? So they run a mile in 5:59, and they just run it one time in 5:59. And they're like, yeah, I always run my miles less than 6 minutes. Like that's my average. And you're like, you ran it in 5:59. That's like you're super close. And like, well, that's lower than 6 minutes. Would that be enough evidence for you if they ran a mile one time in 5:59? Because maybe it's really important. Like we have a new delivery thing on campus, and who's ever going to deliver stuff has to run a mile consistently in less than 6 minutes. And them just doing it one time is probably not a good enough evidence, right? What if they ran it 100 times and their mile time was 5 minutes? You'd be like, wow, that's super evidence. Wow, you've done it 100 times, which is a very large sample, and your average for that 100 times was 5 minutes. So don't just look at, we see a lot of people on the test, and I see this. I literally get answers like this on the test. People will see 12%, which we changed the problem to, and they'll be like, 12% is more than 10, that's evidence. I'll be like, no! You need a z-score. You need a p-value. Because just like your friend who runs the mile in 5:59 one time and says, see, I told you I always run my miles in less than 6 minutes. You're like, well, that's one time and that's barely faster. So we have to do the things, if you look, it's much like you use your sample size and then you figure out what the difference is. Before, when it was almost 24%, that was a huge difference, which was unlikely by random chance, i.e. it had a what p-value before? A very small p-value. Where this time we see a small difference, and the z-score is closer to 0. And the p-value, since the z-score is closer to 0, the p-value is closer, or larger, I should say. It's not really close to 1, but the p-value, if you notice, as this gets closer to 0, the p-value will get larger. As the z-score gets bigger, the p-value gets smaller. Because larger z-scores are what by random chance? More unlikely. They're more unlikely. Does that make sense? Where small z-scores, it's like if you saw someone who's 5'8", you wouldn't be like, whoa. Not that we should judge people by their height and be like, whoa, you're tall, you're short. No. But you'd be like, their height I expect people to be. And that's what you would expect to see. Question?
For a question on the test, would they give us the p-value?
We often have to do this, especially on the test. We might have you look at a graphic and be like, which one of these has your p-value? Or which one of these p-values seems plausible? A multiple choice test question could read for this, and let's think here. If I were to write a multiple choice test question, I'm going to change this again. We're just doing a little, if you notice how quickly I can change this question, because every question is going to have the same structure for testing a proportion. We're just going to change what the x is, what the n is, what the p naught is, right? So let's change this slightly here. And I'm going to cheat. I'm going to have you guys put this in your calculator. Because now it would be 32. And I'm going to tell you guys as best as I can the answer. Don't tell me yet. Okay, I think I got it. And then I'm going to ask you a multiple choice question on p-values. That should be very close.
Yes.
Is that down to the decimal? What's the last decimal now? 83? Okay. Do you know what I did to find that? Think about this. What was the difference on top of the equation when it was 12? What was the difference between these two numbers? What percent? Well, it was 12 and 10. What percent difference was it? 2. And so all I did was take this number, because now the difference is 6, right? 6%. So I took this number right here, and the difference went from 2% to 6%, and I took that number and in my head did what to it? Because the difference went from 2 to 6%, I took that number and I times it by 3. Now, you're not meant to know these things that I'm doing, but I knew the difference was 3 times more, and we're still dividing it by the same number, right? So if the difference is 3 times more, the z-score is 3 times more. So try this in your calculator to be able to solve all these, and you should get this z-score. Now, a test question would read the following way. Let's write a fake test question here, and let's say, what is the p-value? So if we were to test you and say, what is the p-value for this? Here are your possible choices. So we could put a p-value of 0.0001. Okay, because I'm trying to think what it's going to be very close to. I will give a p-value that is plausible, but I don't know if it's the exact p-value. Usually on the test, when we write a test question like this, we actually give the real p-value, so I'm not going to show the real p-value yet. I'm just thinking what it has to be close to. Well, I guess it's going to be very close to that. Okay. 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 And let's do that. Okay, which of these, I'll go off the screen. Which of these p-values would be the only possible p-value it can be? Which of these p-values, I'll go back to it in a half second here. Which of these p-values is the only possible p-value it could be? It can only be B. As you notice, I paused on that one, thought. If you're like, Brian paused on that one and thought for a really long time. Is anyone wondering how they figured that out? Or besides me pausing? So this goes back to the empirical rule. The empirical rule, when we look at this graphic over here, our z-score, I would literally draw my curve and I'd put where I'm at. I'm at right about here, right? Does everyone see that? So if I'm right here, I would shade this portion of the curve. And we'll go ahead and confirm our answer right here. We'll go above, and we'll go to 2.83. And I said 0.004. I should have said 0.002. So we'll round that to 3 decimals, so it looks like that. And we'll change the question here to say this. I was close-ish, but not close enough. I like to be as decimal accurate as I can be. Once again, I was trying to figure out in my head what it could be, but I had a good guesstimate of what it could be. If you notice, I was only 2 thousandths off, right? Not that bad, right? So with this right here, if you look at that small sliver, well, one, what answer just seems ridiculous to you? D. D is just ridiculous. D is like, I drew this out. It's a tiny little sliver at the end of the curve. And some people draw their curves differently, though, right? So maybe they don't see it visually accurate. But here's the thing. When we go back here and we use the 68, 95, 99.7 rule, we can get a very good estimate on the p-value. And the first thing we would do is say between -1 and 1 is what percent of area? 68. Between -2 and 2 is?
95.
And wait, if 95 is between -2 and 2, what is total outside? If 95 is in, total outside is? 5. And in one of my hands is? And wait, so if I shade from here over, I have 2.5, right? And basically, it's not going to round exactly, but around 2.5, that's the perfect decimal accurate. So that has just eliminated what answer here? That eliminates answer C. C has been eliminated because C is also too large. Does that make sense? Because it has to be less than 2.5. So that is obviously less than that. So then let's go to 3. In between -3 and 3 is what percent of area? 99.7, which means total outside is what? Total is 0.3, and one of my hands is worth 0.15. And wait a minute, 0.15 is this? Oops, I made that way too small, because 0.15 in decimal format would be 0.0015. And we know that our answer has to be between 0.0025 and 0.0015. And the only answer that falls between it is B. Does that make sense? By process of elimination, we know that A is too small and B is just right. It's between those two numbers. So that is the area above a z-score of 3, which we can figure out with the empirical rule. And so those are some of the harder questions, I think, in its multiple choice. But drawing it out might help. Drawing would at least eliminate D, I would hope, because it'd be like, that's way too large. And then, but sometimes we can make it tricky, because everyone's like, it's got to be one of those middle answers, right? That's usually what you think, like, math, like, a lot of times when you write tests, there's just, you're like, okay, I got to choose between B and C. It's now it's a 50-50 coin flip. So that goes right there, and what do we see? Well, we've changed this p-value again, and look at all I do. Now all I'm going to do is change I fail to reject to what? I reject. I've changed my p-value here to just what it is. It's now 0.002, and with a p-value of 0.002, as long as that's less than alpha, I reject the null that the true proportion of students who go to Starbucks is 10%. And then what do we say next? I have evidence for the alternative. And so we basically can take this right here and we say, I have evidence for the alternative that the true proportion of students who go to Starbucks is greater than 10%. I have evidence for the alternative that the true proportion of students who go to Starbucks is greater than 10%. The question could read, UT will open another Starbucks if at least 10% of students are going to Starbucks. Would UT have evidence with our new example here to open that next new Starbucks? They would have evidence. They would. In this example now, as I've written it, I know I've changed it a few times. I'm just changing the p-value to where they do have evidence or they don't have evidence. Does that make sense? Just so we can hear both interpretations. But what did you do to your null? You whatted your null here. Go ahead and read what we have. You rejected it. When the p-value is low, reject the null. When the p-value is high, just let it fly. Just let it be. So you rejected the null, and you now have evidence that more than 10% are going to Starbucks. And apparently that's their threshold to open another one, because we'll just, new Starbucks, new Starbucks, new Starbucks. So we have evidence for the alternative that more than 10% are going, and it might say something like UT will open another one if they have evidence of this, and you would say UT has the evidence they need to suggest that more than 10% of students are utilizing this new Starbucks, so they would open another one. Does that make sense? Sometimes we have some actionable thing that they will do if they reject the null, and they do have the evidence they require right here. What else do we have? That right there is pretty much the whole chapter. You guys ready to do another chapter? That was a lot of the chapter with a big example. And go to the next chapter, just next chapter. Do you guys want to do more on tests or a question? Go ahead.
Yeah, so for the original number you used for the,
Yeah, so the null always stayed the same throughout this problem. I kept the null the same, but if you look back, and I'll change it to make it the same example here, I kept changing the number in the sample from 47 to like 20, or I changed the number quite a few times on what X was. The,
7 still you would reject?
no, 47 we would reject on. 47, just to review if you want, 47 gave a z-score of 6.36 and a p-value of 0. So I'll write that quick notation here. I think I remember the values. I might have you guys repeat them to me if needed. When X was 47, X equals 47 gave a z-score of 6.36 or 26? 36. And then it gave a p-value equal to what? And then X, we did like a one that gave 12. We gave 24 in X. X at 24 gave a z-score of 0.94, right? And then a p-value equal to 0.173, I think. And that would be not reject and fail to reject. And then this would be, does this shorthand make sense that I'm writing right here? Fail to reject? Does that make sense? Fail to reject right there. And then the last example we did, so you can kind of practice these and make sure you have them down. The last example we did, I changed the x again. And I think this is kind of neat right here, because what you'll notice, as the z-score gets bigger, you can see the p-value. Maybe we'll put them in order in just a second. Then this was 2 point, and what was it, Muhammad? 8.4? 8.4, and then the p-value was 0.002, right? And we had a 3 there. We'll color it. And if you notice, we'll put them in this order right here. I'm going to remove that. What you'll see is as the z-score gets bigger, the p-value, oops, we got a problem right here, right? Oh, did you see that already? Thank you. Please, please, please catch that if I copy-paste something and don't change what needs to be changed. 2.83? Yeah. Oh, awesome. Thank you. We'll make it as decimal accurate as possible. There we go. So as the z-score gets bigger, the p-value gets what? Smaller. That is so many zeros that it'd be like 0.00000000839. So, do what?
You found the p-value by putting it in the computer, right?
Yeah, so if you guys want, I can tell you the exact p-value of that.
No, it's
Okay. It wouldn't be that. To do that one, I have to use technology we don't use in the class. Give me a half second. I want to know the p-value now. If I don't break my computer.
Is there any way we can go over the hardest chapter you think is on the test?
Which one?
Just the hardest chapter you think.
The hardest. That is a good question on the hardest chapter. I'm going to paste in here the p-value. Ooh, here we go. I got the p-value. The p-value for that one is, let me go back to this. Okay, cool. The p-value is the following, just so you can see it. It's going to break. The p-value is that. That's the p-value. So and I think, so we can find these out, but basically, I mean, for all intents and purposes, that's the chance of basically winning the lottery, right? So basically, do you think your results, this is the probability of our results happening by random chance given the null is true. Do you think your results happen by random chance given the null is true? Because that's the probability they happen by random chance given the null is true. Let me phrase it another way. That's the probability you think you're going to win the lottery. Do you think you're going to win the lottery? Or the probability you'll win the lottery? You don't think you'll win the lottery. That's the probability your results happen by random chance given the null is true. Do you think your results happen by random chance given the null is true? No. It's the same question. Wait. So this is something I like to cover with students, because wait. That's the probability of you winning the lottery with the ticket you just bought. Do you think you'll win the lottery? Okay, so don't, remember, I'm going to mention that same probability. That's the probability your results happen by random chance given the null is true. Do you think your results happen by random chance given the null is true? Correct, you are correct. So because it's the same, like, I do not think my results happen by random chance given the null is true, because that's the probability of that happening. It's telling you that your results were what by random chance given the null is true? Your results were, starts with a U, unlikely. We usually say unlikely. Unusual would mean the same thing too, but it means our results are unlikely. So what do we do if our results are unlikely given the null is true? We reject the null. And that's why we say when there's a low p-value, we reject the null, because our results were unlikely given the null is true. So we're saying, I don't think that null is true because I shouldn't see this if the null is true. Does that make sense? If 80% of students in our sample liked Starbucks and went to Starbucks, should we see that if 10% is true? Is it possible to see 80%? Maybe if we talk to 10 people, right? But even then, it'd be unlikely. So you'd reject 10% and say, I don't think 10% is true. I have evidence against that. Does that make sense? And as we notice here, the bigger the z statistic, the what evidence we have? The bigger z statistic, the more evidence. Because the bigger the z statistic, the what are the p-value? Smaller the p-value. And the smaller the p-value, the more evidence, the stronger the evidence. So the question was the hardest chapter on the test. That's hard for me to say what's the hardest chapter. It's a great question. Depends. What we could do one of my favorite things right now, because I think it's a good switch to do, and this is kind of a good quick review. We'll do the more on test chapter. So we'll write up here more on test. So let's add in here more on test, because we got another. This is chapter 17, I think, and then we'll go back to doing confidence intervals for means and stuff like that. More on tests. So I need somebody, you know what I'm going to say. What I'm going to say, I need someone to what for me? Count. 1, 2. I need someone to give, I hate that. I need someone to give the letters of the alphabet. A, B. I need someone to give the whats? Sides, like sides. Does it see it? Not sizes, but sides of a battery. Does you think like, what two sides of a battery are there? Like, plus and minus. For all the times I've taught this, it's always plus and minus. So what are we talking about right here? One of my favorite things to teach is type 1, type 2 error. So we'll go through this and we're going to remember this. So I'm going to hold this up for a long time for the online people to see. Who knows my saying? In a type what? If you can see right here, I'm holding up a 1. Hopefully they see it. In a type 1, the null is true. And now if the null is true, remember, what two conclusions do we come to in the null? We either what the null? We either reject or fail to reject. Now, in a type 1, the null is true. What would be wrong to do to the null? Reject it. Because if the null is true, right? So what would be the wrong idea here? That is correct. If the null is true, then we should not reject the null. That'd be a mistake. And that'd be a what error. If the null is true and we reject it, that'd be a... If you ever get confused, remember for the second one, in a type 2, the null is false, and we fail to reject it. Does everyone hear the two F's? In a type 2, the null is false, and we fail to reject it. In a type 2, the null is false, and we fail to reject it. And I love these questions, but I hate them, because when we ask them on the test, they're often a coin flip. And I've said that already once, but these are the true coin flip, where students just, and they're like, oh, I reversed it, can I get the coins back? And I'm like, no. It's like it's so easy to reverse the two, right? So let's try 3 examples with this, then we'll talk about power next, and we'll go to the next chapter. This will probably be a 20-minute discussion here, a review of this. Go ahead, question?
Wait, so you failed to reject the type 1?
Go ahead, careful. Repeat it with me. In a type 1, the null is true, and it'd be a mistake to reject it. In a type 2, the null is false, and it'd be a mistake to fail to reject it. Does that make sense? So a type 2 is when we fail to reject the what null. A type 2 is when we fail to reject a false null. A type 1 is when we reject a true null. Does that make sense? So it's just memorization, I hate to say. It's in a type 1, the null is true, so you've got your T right here, and we reject it. In a type 2, the null is false, and we fail to reject it. And you just have to repeat it like that. Remember, each statement is about the null. Don't mention the alternative. Don't say that. Just in a type 1, the null is true, and we reject it. In a type 2, the null is false, and we fail to reject it. So type 2 is failing to reject a false null. A type 1 is rejecting a true null. So pause and go slowly and practice saying it. And we're going to do some examples here, and we did this in my office yesterday, and there was lots of debate. So let's write out one of my favorite examples here. I've done this many times, where we do the example where we see if you're cheating. What would be a good null hypothesis for people cheating? A good null for people cheating would be that what? Not cheating. We'll go with not cheating. If I use the null that people are cheating, I would say, bring me evidence you're not cheating. Does your teacher, if you're caught cheating, then they'd say, I need evidence you're not cheating. But usually you would say, I need evidence someone is cheating. You wouldn't say, I need evidence they're not cheating. So usually it's innocent until proven guilty. It's the same way. Now be very careful, and then I'll show you how I do this. Be very careful, but here we go with the type 1, type 2. I want you to tell me which of these errors would you, as a bad student, you're not a bad student, but if you're a bad student, which of these errors would you really dislike? I guess, wait a minute. No, let me change that. As a good student, there we go. As a good student, which of these errors would you really dislike? Oh, you see, everyone says it. No, that's what I hear. Everyone's like, type 1, no, type 2, no, type 1, 2. Pause. Okay, here's what we have to do. Let me repeat the question. As a good student, which of these errors would you really dislike? As a good student, which of... Oh, there's debate.
You said like or not like?
As a good student, which of these errors would you really dislike? So the question is, as a good student... All right, we got some confidence. Are you ready? I think you're right. I like the confidence there. And here's what I do. To confirm this, I say the same. I look at that null, and I say in a type 1, I look at it and I say, the null is true. Does everyone see what I'm looking at? I look at it and I say, in a type 1, it is true that I'm not cheating. Does that make sense? And what is the teacher going to do? Reject it. And they're going to say we're cheating. Does that make sense? Look at the null and say to yourself, that is true, but we're rejecting it. So what is true about the student? They are not cheating. But what are we going to do that in a type 1? We are going to reject it. So in a type 1, we accuse a non-cheater, a person who's not cheating, because that's true, and we say they are cheating. And so in a type 2, the null is false. So in a type 2, they're cheating. So look at the null in a type 2 and say, it is false that they are not cheating. That is false. But what are we going to do in a type 2? We are going to fail to reject it. So we're going to conclude in a type 2 that they are not cheating. Thank you guys. Everyone said it. And so we're going to conclude they're not cheating when they are cheating. Does that make sense? Okay, let's do my tree example here. And we got a tree. This is from an old test. And we're going to do 2 more examples. Practice up, because we can never practice these enough. They're so easy to switch. We got this tree leaning down. It's your favorite tree. Well, actually, this tree, it looks like it's really going to hit your house. So we're going to chop down the tree. We're going to chop down tree. Or we're going to leave up the tree. Because that tree, you've had a lot of trees fall recently in your yard. I mean, and this tree is leaning towards your house. So what's the safest thing to do? Chop. But your kids, this is 20 years from now. The kids are like, come on, Mom, Dad. They're like, we love that tree. That's the tree you got married under. And you're like, yeah, I know. It's like, it's a long story. It's the whole problem. You got married under that tree. You want to leave the tree up. So you're like, I want to leave this tree up, right? So, but the problem is, you would need what to leave that tree up at this point? You would need what to leave that tree up? Evidence. So think about what you could do. You could take soil samples around the tree. You could take root samples. You could, if the tree has limbs falling, or you could test the limbs. You could pull on the limbs, right? So, and then the limb like rips off and the tree starts falling. Okay, that was a bad idea. So you could do things to find evidence the tree is still healthy. Everybody take 15 seconds at least. No one say an answer. Do what I told you to do. Do what I told you to do. Sorry, it's a joke. And look at the null and tell me what are the consequences of a type 1 error. So don't say it yet. Don't say it yet. I want someone, after we take this time to think about it, I want someone to very carefully look at it and tell me, in a type 1 Brian, this would happen, but blah, blah, blah would be blah, blah, blah. In a type 1 error, just be very careful. I'm not even going to think about it. I'm going to let you tell me the answer, because these are very easy to switch. I mean, you can probably tell. One of them is you're going to chop down a healthy tree, and one of them is you're going to leave up a dead tree, right? And that's the errors, but then you have to figure out which is which way. Okay, we got you got it so well last time. I'm actually going to, okay, we're going to go to you. You get to say right or wrong when someone gives the answer. Got it? No, that you were so sure that I was like, you have to be right. Type 1. All right, so we have Julia. Okay, so we're thinking of the consequences of a type 1 error. Be very slow. Okay, ready? Go ahead. And then I'll repeat it, because they can probably only hear me. So if you hear me repeat answers, that's why I often, after you guys say things, I repeat to the microphone here.
So wait, type 1 is...
All right, so be very slow. Before you say your answer, pretend this is the test, and you only get one shot.
So you would reject the true null for type 1, so you would not chop down the tree that you should chop down. You would leave the tree. You would leave a dead tree when you should chop it down.
Is that correct? That is correct. There was no one even arguing in the class right now because you looked at that null and you said it is true that we should chop down that tree, right? But then what do we do to the null? We reject it, so we say we should leave it up. Does that make sense? So in a type 1, the null is true, but we reject it. We say we have evidence. It's like we let someone come out and they're like, oh, that tree's healthy, and we're like, okay, we'll leave it up. And so in which of these errors would you find out that you made the error? Which of these errors would you find out? Only? Wait, you just said in a type 1, you leave up a dead tree. In a type 2, we just have to flip it now. You chop down a healthy tree. In a type 2, you tell the stories years from now, man, I'm so glad we chopped down that tree, it would have fell on the house. But it turns out that tree you chopped down was healthy. In this instance, the way I've written it, if you look back at the Old Testament, it might have flipped what the null alternative was. Watch out, I'm just speaking to this example. So would you ever find out the type 2 error? You chop down a healthy tree, would you find out your error? Someone might say, maybe you'd find it out because as you're chopping it down, it's like this super rich and healthy and sappy tree. Maybe sap's healthy, I don't know. But you'd probably be like, it would have probably fell anyways. It looks healthy, but nah, I'm glad we chopped it down. But in a type 1 error, you find out your mistake because the tree's probably going to fall. You're probably just going to get worse, and you're going to eventually be like, okay, we need to chop it down. So the tree is dying, and you should chop it down. Last one right here. You guys want to go on those pirate adventures? Let's go on those pirate adventures. So we got our last example here to cover type 1, type 2 error, then we'll do power next. So we're doing the pirate adventure thing here. So how does it usually work? When you go to the doctor, when you walk into the doctor, what is their null for pretty much any sickness? Do they walk in and they test to say, okay, we need to test to make sure you don't have measles right now. We need to test to make sure you don't. Is that the way you guys do it in medicine? You test to see if people don't have stuff? What do you usually do? Evidence if they do have stuff. So you look for evidence that they have it. And actually, false positives in medicine, have you ever heard of that? Yep, that means, and it's going to be really easy to do this example because the null would be that you do not have scurvy. You're a pirate. And doctor doesn't know that. They maybe think you have scurvy if you are a pirate. And the alternative would be you do have scurvy, which actually, when you know what a false positive means in medicine, it makes this one super easy, right? So what does a false positive mean? Just go with your knowledge with this is something we're testing for. It's a false positive. It means what? It's a false positive. False positive. They tell you you do, but you actually don't. Where a false negative means they tell you you don't, and you actually do. The test comes back negative. Does that make sense? You're like, man, I've been feeling like my vitamin C's all low. I don't know how I feel that, but apparently I do. And you get tested, and they're like, you're fine, but it turns out you aren't fine. So they come back with a negative result. Because think, in a type 2, the null is what? False. But we fail to reject it. So it is false. Look at that. It is false that I don't have scurvy. So I actually have scurvy. But what do we do to the null? We, in a type 2, fail to reject it. So I'd say I do not have scurvy. So we would conclude they do not have scurvy when they actually do. And that's why I wrote at the start of this, positive, negative. Because in a type 1, I call it a false positive sometimes. Just depends on how you're testing it. You have to watch out because if you had somebody who's trying to get treatment, let's say someone comes in and they're doing cancer treatments or something like that, then what would you look for? Evidence they still have cancer, or like just think in the medical industry. If we know someone is sick with something, we often look for evidence of what? Do what? I would say evidence for remission maybe. Does that make sense? Because you're looking for evidence to take them off treatment at this point. Because it kind of switches the null. Does that make sense? The null is just whatever your initial belief is. I could think everyone's cheaters and say, I need evidence they're not cheaters. Have you ever heard of a class where the teacher says, you're all cheaters, you're all getting zeros unless you can, it's like, whoa. They've switched the null, right? We're all guilty till we can prove we're innocent. You can do that. The null is just an initial belief. The null is what you started believing. Oh my gosh, that's so glad. I'm glad, Chelsea. And I actually see it streaming decently. I can see that. Thank you, Chelsea. We got 5 people watching. Woohoo! But I hope this gets utilized a lot more over the weekend because we're going point by point. Do you guys feel this is good? Yes. All right, good. We're just going topic by topic, chapter by chapter. So we got this right here. We know what the nulls and alternatives are. UT turned back on the internet, so we like that. Okay, let's do power for a moment. There are 3 things that impact power. The 3 things that impact power are, so let's write here, 3 things that impact power. And the 3 things that impact power are effect size, and we'll mention them all. Effect size is the hard one. So we have here effect size, what else? Effect size, sample size, and alpha. And power is actually the formula 1 minus beta. Power is the formula 1 minus beta. Basically, power is the ability to reject the null when it's false. It's the ability to find results. And think about this. When we do our tests for sicknesses, we want to be able to reject the null, right? So think about a powerful test in medicine. It'd basically be able to identify the people who are what? A powerful test in medicine would be able to identify the sick people. And do you know the most powerful way to figure out who all is sick and find every sick person would be? It'd be to change your what? Alpha. Now that's playing games. Because if you set your alpha, let's put some values right here. We'll do some ridiculous stuff. Would this be a very powerful test right here? Would that be powerful? That's the opposite of power. That is a very weak. So, and then I'll mention this is regular, this is probably you shouldn't do, and we'll put a ridiculous one here. Now I'm going to mention, and was there a question?
Yeah, kind of. On the practice test, it has like a question about power.
What's it say about power?
Like just like I think I asked the straight up definition.
The power is the ability to correctly reject the false null. Power is the ability, sometimes we have that correctly. I hope if we ever give the definition again, we give as close to the actual textbook definition. Power is the ability to correctly reject the false null. Power is the ability to correctly reject the false null. I like it in the more practical sense. Power is the ability to find results, but that's turning into something kind of colloquial that people can understand. But power is the ability to correctly reject the false null. And we should reject the null when we should. Because think about this. What error is this? We say reject the false null. This is when we what the? And a type 2 is when we what? Fail to reject the false null. So what hurts power is when we don't reject the false null. So if we were to reject the null every time that we should, how many type 2s would we make? We'd make, if we were to reject the null every time we should and made no type 2 errors, and then what would power be? Well, beta would be 0, right? Because we'd make no type 2 errors, and then power would be the highest it can be. 1 is the highest power you can have. It's our ability to find results. Like, if power is very low, you can't find results. And just think about this. Let's think about this mechanically right here for a moment. I like using, we'll go through a few examples here, and I'll hopefully help you guys understand why power works this way. I like to talk about playing my brother in basketball or my friend LeBron in basketball. So just think about that for a moment. Brian's going to play his friend LeBron. We're friends. We go way back. I used to live in Ohio. This is all lies. And so he's from Ohio, right? I mean, I should know he's my friend, but sometimes I forget these things. Is that right? LeBron? James?
I don't watch sports, so I don't know.
He's from Ohio. Oh, yeah. Okay. If someone watches sports less than me, that's impressive. So you might win that right there. So yeah, LeBron, my friend LeBron from Ohio. Imagine you were to watch me play my brother or me play LeBron. Who would it be easier to tell that there's a difference between these two people? When you watch me play LeBron. And so which of these concepts might that relate to? It relates to the first one, effect size. Because the null, and I know this sounds crazy, but if you watch two people play basketball who you don't know, what would you assume about their abilities? That they're equal. So that's the null. The effect size is the difference between the null and the truth. So the effect size is the difference between the null and the truth. So if my brother and I are very similar in basketball, I mean, do you think we're exactly the same? Like, we are 100% equal ability, my brother and I. No. One of us is probably a little better, right? But we're brothers. We probably played each other in basketball. I steal from him. He steals from me. He dunks on me. I hit the rim when I try to do a layup. Fall down. Game over. But with this in mind, it'd be way easier to see with LeBron, right? Because the null of us being the same is ridiculously false, right? It's like you assumed Brian and LeBron were the same, but the truth is that they're very different. And so that difference right there is very easy to see. I also like to use the hospital example again. So what is the null for everyone walking into the hospital? We just talked about this. They are what? Just think of one word. Someone walks into a hospital. You would say, you're sick, I know it. You would say, you're healthy. Let's see if there's evidence you're sick. Does that make sense? So we'd look for evidence of sickness in a hospital. Of course, you're at a hospital. We need to do tests, but we're trying to see what you have. We don't say you have this, this, this. We're trying to rule them out. I mean, that's what we do with a test, but we'd look for evidence they have that, not saying you have it and start putting you on medicine and then saying, okay, the test came back, you don't have it, stop taking that medicine. We usually look to see if you have it, then give the medicine. So with that in mind, think of this. If we change the effect size, how would that work in the hospital scenario? The null is that someone's healthy, and so Julia just coughed one time. Sorry, Julia, to call you out. She coughed once, she went, ahem. Is Julia sick? Oh my gosh. No, that's a very what? Very large or small effect size. Very small effect size. So if she is, it's very hard to detect right now. We're not saying you are, but it'd be very hard. Sorry, so that's when you're my students. But what if Brian were just to collapse right now and my nursing majors came over and they realize I'm sweating, I'm 102 temperature, my pulse is still radiating, I'm in tachycardia, like all these things, like you're like, something's wrong with Brian, right? And then Julia looks over and she says, You'd be like, no, the effect size here is so huge. Because when is it easier to detect someone is sick? When is it easier to reject? Because the null is that I'm healthy right now. You look at me, you say, Brian's healthy, right? But you need evidence to reject the null. But when someone coughs one time, that's probably not enough evidence. I mean, it's not that it's the evidence, it's that the truth that maybe they're a tiny bit sick is very hard to detect. But when somebody is super sick, is that easy to detect? And all we're changing here by saying you're sick, but you're only coughing once, or you're sick and you're passed out and your heart's racing. Which of those is easier to detect? When they're super sick, right? And all I'm changing here is the what? The effect size. Does that make sense? Just like when you watch me play my brother in basketball, there's a difference, but it's hard to see. Or me playing LeBron, there's a difference and it's super obvious. It's the effect size. Question?
So on the practice exam, the symbol for type 2 is
Beta, and it's more of a B beta. Maybe I should put in there. Let's add in the real symbol. You are correct. I don't want people to think it's just B. It is actually a beta.
So then what's the 1 minus beta?
Power. That is the equation for power. That is the direct equation for power. So 1, do you guys see my beta up here? It should just look like a B.
1 minus alpha.
It's a capital beta. Sure. Okay, that looks just like a B. Do what? No, that is a beta.
Yeah.
That is a beta. It just looks like a B. I thought it did. Let's just try one more time here. Yeah, I usually see it with a little bit of a tail. Maybe lowercase beta and capital beta are a little bit different.
Yeah.
But so tell me if you guys see beta up here.
Yes.
Yes.
Oh, it's right here, right? That's beta. That's the one we use right there. It's got the little tail. So I think that's lowercase beta, and we use lowercase beta. And then, of course, right here, so we'll copy this up to here. So type 1 error is actually your what level? Alpha. And so this is actually, so let's go to insert, equation. The lag is what happens when you stream and do all stuff. And do you guys see alpha? Where's my?
Yeah, it's next to beta.
Oh, of course. Is that literally the Greek alphabet going from alpha, beta? I shouldn't. Is that lambda? Gamma. Dang it. Delta. Epsilon variant. I don't know my Greek letters nearly well enough. I just know the ones we use most often in statistics. So alpha is your what error? Type 1. So if you increase your type 1, you decrease your type 2. And what's the easiest way, especially during a quarantine, to make sure you find all the sick people? To just say, you're all sick. And what have you done there? You've increased the alpha of your test. You're basically saying, alpha is your threshold of the evidence you need. And if you put that all the way to the top, you don't even care about evidence. Because think, you need a p-value what to alpha to reject the null? Lower than alpha, right? So now actually, the way it would actually work with a alpha of 1.0 is unless someone's perfectly healthy, like it's quarantine, and you go like this, you're like, you touched your nose, you're sick. You're like, I'm fine. You're like, that's evidence. And you'd think you'd probably make a lot of what errors here? Think it's alpha. Type 1, because that's how we do 1, 2, A, B, plus, minus, because you'd say, you touched your nose, you're sick, sounds like I'm telling someone they're sick when they're not. So that's a type 1 error. And literally with an alpha of 1.0, any p-value below that, which this is not the way we do statistics, but it kind of works with the idea of a quarantine, like anyone who shows any symptoms, right? Any sign, like you have 100.1 fever, 100.1, you're sick, or 99, even a little bit above 98.6, you're sick, you're staying inside. And it's kind of crazy, but I mean, we do have instances like this where it's like anyone showing any signs, you're quarantined, right? You have to do that. We've been watching a lot of Resident, so they do stuff like that. Maybe that's not how medical things really work. Okay, so wait, you guys got to hear this, especially for nursing people. They were about to do a surgery, and Chelsea pointed this out. The guy on the Resident was holding the hand. He was going to be part of the surgery. He was holding the hand of the person they were going to do surgery with right before doing surgery with his sterile gloves on. So he was holding their hand with sterile gloves on. And Chelsea was like, he's wearing sterile gloves. Why is he holding her hand? Because she's not sterile. And yeah, so I just it's fun watching shows with her like that because the medical stuff, it's like why. One of the guys went to open a door and he put his hand against the door with sterile gloves on. She's like, what is he doing? So that hospital on the Resident and he's the chief of surgery, CEO and chief of surgery of the hospital, and it's a lot of fun. All right, so I think we covered alpha. Does everyone know what alpha is? Alpha is the percent of time you reject the null, and if you reject the null more often, you'll fail to reject it less often. Does that make sense? Your type 2 goes down. You have less type 2, which is fail to reject the null when you should.
So you said the alpha is the percent of the time.
Alpha is your willingness to reject the null and make type 1 errors. Alpha is literally type 1 error. That's why I have it right here. I think this is a good chart to remember. It's pretty easy. But alpha is literally your type 1 error. And if you increase type 1, you decrease type 2. Now, they're not complements. It's not like alpha's 0.05, beta's 0.95. It'd make life too easy, right? So alpha and beta are inversely related, but not complements. But if you increase your type 1, you decrease your type 2. So when alpha goes down, beta goes up. When alpha goes up, beta goes down. And I guess I should say this. Let's try this. You ready? It's something I practice. But when alpha goes up, beta goes down, and I need a third hand over here. If alpha goes up, beta goes down, and power goes up. They're all inversely related. Because as you'll see on the slides right here, as I've written, power is literally the complement of beta. So power is literally not making a type 2 error. Back when we used to do complements, power is not making a type 2 error. The only other one is the sample size we haven't talked about much right here. And the sample size is literally how much you cover. So let me write, like Mohammed asked, probability of type 1 error. That's your alpha. Also your rejection criteria. Because it's at what point you'll reject the null. Does that make sense? Because your p-value also has to be what to alpha to reject the null. 5%. No, wait. We say when the p-value is low, reject the null. But what is the full saying? When the p-value is lower than alpha, reject the null. Do you remember that? So what is usually alpha? Alpha is usually, and it's on the screen, alpha is usually 0.05. Alpha is usually 0.05 unless otherwise specified, but you can pick any alpha you want. Does that make sense? So could you increase your alpha? And that would make your test what? More Higher alpha, lower type 2, lower type 2, higher power. Because when alpha goes up, power goes up. Beta goes down, power goes up. Now sample size, think about this. Would it be easier to tell someone's sick if you took a drop of blood, a vial of blood, or 5 vials of blood? Which would be easier to tell? What would it be? 5 vials of blood. You could run a whole bunch of tests, right? When would it be easier to see who's better in basketball? If you watch 1 second of me playing my brother in basketball, or you suffer through 1 hour of it? 1 hour. And what am I changing here? No. The sample size. I'm changing the sample size. How much you take, how much data you take, right? So if you were to watch me play my brother for 1 second, it'd be really hard to make a decision. It's like earlier, remember when I said if we talked to one student, could we really come up with results from that? No, that doesn't have enough statistical power. And so if you talk to one student, you probably couldn't find results. It used to be too hot in these rooms, and then they're like, let's turn that air on full blast. And I'm like, woo, it's cold in here. So if you talk to more students, you're better able to find results. So with a larger sample size, you have more statistical power. And I think that fully covers pretty much a lot of these topics. You guys ready to head on to the next topic and do some one sample means? We got time. I think we're getting, is it almost close to 2? We're going to try to do 1 sample mean, 2 sample means, and try to do chi-squared and get everything done by 3. How's that sound? Let's do it. Remember, the first, go ahead, question? Yeah.
You said sample size,
Larger sample size, larger power. All of these are increased with power. Larger sample size, more power. Larger alpha, more power. Larger alpha, more power. Larger effect size, more power. Larger sample size, more power. These are all, they go in sync with power. So that's what we have there. Let's go ahead and do one sample means. We're going to do some tests and intervals, so we're going to do a big problem right here where we do the test and intervals. And I think we did this earlier, so remember we already have one question. No, yeah, we did. We did a question earlier, so we did a confidence interval. So let's do a test, right? And so what I'm actually going to do to make sure we can do this nice and quick, we didn't do a test. I mean, we did a confidence interval. So I'm going to I'm going to choose to test the value of 87. So I want you guys to realize, for those who have already watched up to this in the video or who were here last time in class, I just want you to look at the results we have, which is in the video, where we made a one sample mean confidence interval, and we said I am 95% confident. The true score students think they will get on the test, the true mean score students think they will get on the test, is contained in the interval 83.61 to 86.39. What I'm going to do for this is I'm going to do a statistical test, and I'm going to test the value of 87. So you should kind of know where this is going to go, and I'll let you kind of follow along as we do this. We're going to take the same question we had previously, and we're just going to drop it in here, and we've already got our notation kind of marked. And remember, we started off today doing a notation quiz. So watch the video, or make sure you record it as I say it. But we've already marked our notation in this problem, and now it says create a 95% confidence interval. Let's change the ending of this question to say we want to test to see if students think they will make, ooh, nice job, Mark, remember, in 87. So we have to pause here. You guys ready? You know what I'm going to say next, right? Because we're starting at the beginning of a problem. What am I going to say? Condition 1. Random. Do you know what we already have marked? Random. You know what I'm going to do? I'm going to go right back to here, and I'm going to grab my conditions. I'm going to grab this right here, and I'm only going to do the first 2. Condition 1. Random. Condition 2. Less than 10%. So we have our conditions right here, and let me put this to a new page break. And we've got a problem. We took a random sample because the problem says so. Once again, we make that as clear as possible in the test, bless you. And we do really well to make sure you know we meet this condition. Condition 2, we said 200, and this one is iffy because it's 200 students, right? Let's say test 3, which is given to all UT students. Now I've changed it so the population is what? All UT students. Don't worry, it's a little bit of a weird problem. It's just that now we have test 3 is given to all UT students. Does that make sense? So we're giving a test to all UT students. And once again, when you're copying this down, make sure to take the notation down because that's going to be the key of it. Because I can change all these little things, just like me turning dials, right? So actually, I don't have one thing highlighted in the notation because it's new. What do I not have highlighted in my notation? 87. Especially whenever you see a number, try to figure out what that number is. And actually, I want to highlight one more thing that'll help us on our next condition. One more thing. Because after we do condition 1, condition 2, we do what next? Condition 1, condition 2, pause, stop, slow your mind. Don't write that third condition just like that, because the third condition is where things change. I always do the first conditions the same. There are no numbers to these conditions. It's just that these are the same for each thing. So why not say them first? So when we get to this third condition right here, we have to think, what kind of data is this? And maybe doing the notation will help us here, right? So let's do some notation for a moment. Well, 200 right here is going to be what? N. Well, N doesn't really help us because that's a lot of questions of N, right? So N is not going to super help us. What else do we have elsewise here? We got N equals, I think Mubarak's got the next one. N equals 200. And then what else do we have? 85. What? Now, a lot of people make a mistake on 85, but I think I got faith in you. What is 85? You are very correct. 85 is Y bar because that is and we reviewed it earlier, I think you said it?
Yeah, it says the average.
The average, and it's the sample mean, right? It's the sample mean. Why is it not mu? I mean, mu is an average. Mu is the true mean, and we'll do the next one. Mu naught is the hypothesized. So y bar equals to 85, and then we just got a little bit more notation. Let's not, we'll do it, sure, why not? What do you guys want to do next, notation-wise? Standard deviation. So that's S equals, did it capitalize? Of course it did. S equals 10, is it? S equals 10, and so what is final last but not least? Mu naught. And let's insert, and let's go to equation. And we got to go over here to mu whenever it appears. And mu. This computer is like, why are you doing this to me? Mu. Uh-oh. Got to go mu naught. Oh, we can do that. Let's go a little. Can I not do that right here? Wait. 2 seconds, everyone. Well, let's go cheat. You ready? Go all the way back up here and grab our symbol, mu naught. And then we copy that. And mu naught is the hypothesized value. And let's bring it back down to right here. Okay. And paste. Done. Mu naught. And equals what? 87. And then I think we have it. So if you notice, question, go ahead.
Why is it y bar equals 85 if,
Hopefully I didn't make a mistake.
what's the difference between y bar?
And mu naught? Sure. And we're going to go back to the notation for just a second. Definitely review this, and great question, because this is where it's really great when you know it, like, boom, because even it's so easy to switch, like, what does the sample mean, the hypothesized mean, the true mean. So the Greek letters like sigma and mu are for population. But whenever we put a little 0 on it, it means it's a what? It means it's a hypothesized, which goes with the null, right? It's a hypothesized value. So whenever you see that little O right there, it would be a hypothesized. And we mentioned this earlier. What if I took this little O right here, this little naught, and put it right here on this? Whoops, not like that. What if I put this little O right next to it? What would this become then? It wouldn't be the true standard deviation. It would become the hypothesize. And we won't do that in this class, but all this would be, if you want for another class, if you saw that, that would just be the hypothesized standard deviation. So it's what someone is saying, well, let's see if this is true. They didn't find it in a sample. They just came up with it. When I chose 87, it's not like I actually collected data. I'm just saying, do I think 87 is true? So if you put the little O on something, it means the hypothesized value of it. So you can also say, I guess you could read mu naught as the hypothesized true proportion. So mu naught, there we are here, is the hypothesized true mean. We were flipping around a little bit. The hypothesized true mean. And it's what we hypothesize the mean is, which is the truth for everybody. So it's just a value I came up with. We want to test to see if students think they will make an 87. Does that make sense? So that is what I'm testing, and that's what we hypothesize is true. So the third condition, now that we have notation, we know that all this data I'm dealing with is what kind of, oh my, that's going to be loud in the recording. It is quantitative. And when we have quantitative data, the third condition is what? Nearly normal. So third condition is nearly normal, and there will be something. So there is something in here right now which is going to help us determine if it's nearly normal. And this is a review from last one also. It doesn't like it. There we go, right there, slightly left skew. And so let's review probably my favorite way to do this. There are a few other ways, but we'll handle one of the top ways to do it right now. With this right here, we are actually concerned about the distribution of the sample mean. The distribution itself is what? The distribution we have is slightly skewed to the left. So is that normal? No, it's not. But we're not concerned about this distribution. We're concerned about the distribution of the sample mean. Sorry, it's statistical theory. Like, what are you even talking about, Brian? What we're, yes, that's what. And so we're not concerned about this one. We're concerned about the distribution of the sample mean. But good thing for us, we have a theorem called the central limit theorem. The central limit theorem states that the distribution of the sample mean becomes more normal and tighter by a factor of the square root of n as n gets larger. So we would have here that our distribution will be tighter, and normal enough, right? This is the large enough n condition of the central limit theorem. So we need to look at this and think three things. Here's the three things I asked you to check. 1, look at the shape of your distribution. My distribution is what? Slightly skewed. 2, remember the number for that condition. In my class, I like for us to use 1 if it's normal, 25 if it's skewed, and 100 if it's heavily skewed or very skewed. And the words can change. Since this is slightly skewed, which number do you think I'll use? And that was 1, I'll repeat it real briefly because I said very quickly there, 1, 25, 100. Normal, skewed, and heavily skewed. It just goes in that order. The more skewed it is, the wider n needs to be. The more skewed, the larger n needs to be. That's why it's called large enough, because the more skewed it is, the larger n needs to be. Think of this. If my hands look like this and they're really not normal, will it take a lot of movement for me to make them normal again? So if my hands look a little skewed, will it take a lot of movement? No, and the larger n is, the more it's like reshaping it. So the larger n is, what if I said, like, let's expand from this class. My distribution is ridiculously skewed, like more skewed than I've ever seen anything. What n might we need at that point? A really, really big one, maybe like 500. Now, pretend I didn't say that, because in this class we just go for simpler ideas, right? That's why we keep it to like 25, 100, and we have techniques outside of this class that we'd use, but we're not trying to teach you everything in this class. But obviously, the more skewed it is, the larger n needs to be. And that's all we're saying right here, because if it's normal, n could be what? 1. If it's skewed, n should be 25. And if it's heavily skewed, 100. And we'll try to, I try to write the keys and make it as clear as possible that if you say something like 40, that's basically the same. There are no exact numbers for these things. No one wrote these numbers in stone. They don't magically become normal at 40. It's not like they're skewed and then you go to 40 and it goes normal. It's kind of an iffy thing that we teach in a certain way in 201. But it's not iffy. I could show you all the math behind it. It's the central limit theorem. So with this in mind, we got condition 3 here. And remember, the first thing is we have to denote its shape, right? The second thing is we have to know the condition. The final thing we need to know is what? Our sample size, and that's it. Listen as I say all three of these things in my answer to the question. Or do this, and I really mean this. Try writing your answer right now. Try writing an answer. What would you write on the test for this? Try writing your answer. I want to hear it from you guys. I want to hear you guys. If you're watching these videos, pause these videos, write your answer, see if you could write it, and see if what you write is close to what I say. Who can do it? Who can tell me their answer?
Yes, for what?
For the condition 3.
Oh, okay.
What was the third thing?
We look at the first thing in this condition, look at the shape, then know the rule for that shape, like what the sample size needed, then look at your sample size. So the shape, the required sample size, and then your sample size. I should have been like, we are not broadcasting this on YouTube. Then like a ton of people show up and I'm like, oh, we're broadcasting it on YouTube. This is, it's so funny what you guys are seeing now is a bit of like the things we've been dealing with the new online class we're doing, because that's why we ordered the really, really, really good computer, because when I'm teaching with the new online class, we can't have it being like 2 frames a second when I'm moving. So the computer we have is really, really powerful for the new online class, because if to do all this like video encoding, it really, if you notice, like Microsoft Word is having trouble right now, so that's when you're reaching trouble. Who has a good answer for condition 3 on this?
The shape of the normal curve is.
Or don't call it a normal curve yet. The shape of the distribution is.
The shape of the distribution is normal enough because.
Oh yeah. Keep going. You're good. Good.
Size is larger than 25.
All right. A nice grader might be nice to you. Here. Oh wait. Good.
The shape of the distribution is normal enough because the sample size is large enough.
Closer, but remember the 3 things you should mention. What was missing? So you might not be able to hear it online, but what was missing in that answer? The 3 things we must mention. There was one that was really missing. I didn't hear the requirement, and I also didn't hear the what's the first thing we need to tell someone? The shape of it, right? The distribution is what? Is slightly skewed. This means we need a sample size of at least 25. Our sample size is 200. Does that make sense? Did everyone hear that right there? The distribution is slightly skewed. That means we need a sample size of at least 25. Our sample size is 200. Did everyone hear that? We mentioned the 3 things, and probably some graders might be nice. It's like this is a really crazy one because this is the central limit theorem, one of the big backbones of statistics, but we need to mention those 3 things. So nearly normal, check 3 things. Please, wait. Okay, so it's like very hard to write this one out, and it's very hard to practice. As you guys notice, this is the condition where a lot of people trip up. But be able to write this out, be able to practice it, look over the practice test, like how they word it, look over how I just worded it now. And like I don't want someone, if someone wrote on the test, check 3 things, shape of distribution, rule for this shape, your sample size. That's kind of the step-by-step process, right? Like you'll pretty much compose a sentence with that. Like, this distribution is skewed slightly, which means our sample size needs to be at least 25, and our sample size is 200, which means we meet the condition. That's a well-composed sentence from what I've put up here. So I'm really worried someone on the test will be like, Brian told me to write that, and they'll be like, what? No, that's kind of the process by which we do it.
Brian,
Do it?
when it comes to the null and the alternative.
Yes, let's write that null and null alternative, right?
Yeah.
So to write the null alternative, the null, when we write it in statistical notation, always has the equal sign. Null always has that equal sign. Yes, Chelsea, thank you so much answering those questions online. I watched Chelsea be 5 minutes behind. That'd be so crazy. I'm so excited about streaming, but I'm so afraid, like, because we've been running so many like hidden lectures of it, like doing like secret streams on the YouTube channel. So what I'm writing right here is the general form. This is the general mu equals mu naught. What we need to do now is we need to put our hypothesized value, and you can still see it, or you can't. The hypothesized value was what? 87. And we have just written our null. We have just written our null hypothesis. We have stated that the true mean score for Stat 1 students, or the true mean score on exam 3, because this is for like all students, is 87. Does that make sense? Now, what do we have for an alternative now? What is our alternative? Not equal to, because the question gave no preference. So the question did not give a sidedness to the question. So the question, whenever it appears, is going to be not equal to. And someone might say, why? Because the only thing I asked is, we want to see if students think they will make an 87. So if I don't give a nature of that to say, do students think they'll make more than an 87, less than an 87, higher than an 87, there is no sidedness. So this is a two-sided test. And as we've been saying repeatedly, when we do the alternative, what is the only thing we change? The sign. I can't tell you how many tests I see where over here I see here y bar. Where here I see 85. And I'm like, no, it's just a whole bunch of different numbers. If you put mu here, you put mu here. If you put 87 here, you put 87 here. The null always has the equal sign, and then the alternative sign is based on the question. Practice that. So if you notice, we've actually written 2 of the nulls and alternatives in statistical notation today. We'll do the final 2 before time's up. So with this in mind right here, all we need to do is grab our equation. I'm actually going to steal a good bit of our previous equation from way earlier. If you notice, whenever we do a statistical test, it's always a difference standardized. Well, I guess I didn't. That is the standard error. And let's go ahead and take, and we need to insert an equation. I am now going to solve for t with n minus 1 degrees of freedom. So I'm going to solve for the t statistic. This t does not have a star on the equation sheet. This is not the t for a confidence interval. So this is the t I am solving for. And we need to then take a difference and standardize it. So I literally have this right here, which I guess we already have. Let me put that in notation. This is S. This is N, exactly. And then the top of it is the difference, which will be what? We're going to take a difference between 2 numbers. No. Minus what? Mu naught. Make sure to only look at the notation you have as you identify through your notation. And every time you say P, you should think what? Every time you say P, proportion, P is proportion. Just make sure. It's all right. I think since we learned to do the null and alternative first with proportions, a lot of people always put P hat minus P naught up there because it's the first thing you learn. So I hear a lot of, P naught when people do that. They're like, P naught. I'm like, no, mu naught. Because we have a sample mean minus the hypothesized mean. That'll give us a difference. And then the bottom, just what's that difference? Standardizes it. And what do we call this right here, just that whole thing? The standard error. Standard error. That's the standard error. So let's go ahead. And I'm going to kind of cheat in my head. I'm thinking here, well, I kind of know the answer too. Oh, man. Whew. Let's see. I think I even know what the p-value will be. Let's take this equation. Let's put in our numbers. It was 85, I believe. 85. And then right here, 87. Wrong buttons. I hit fast forward rewind. And then here is 10. Do this on your calculator and see what you get. I think, did you already do it? Don't tell me what you got yet. Did you get a z-score of really close to like 2.5? T-score. 2.5-ish? Oh, no, what'd you get for the T? 2.83? Ah, see, I'm getting worse as time goes on. 2.83. So see if you did on your calculator. This is also t-test on your calculator. On your calculator, did you do it on t-test? Yep. So on your calculator, this is t-test. So if you're doing it on the TI calculator, you can do it on t-test. As you can tell, the equations are not that hard to plug numbers into. I've memorized these equations. They're not that crazy. If you notice, every equation I do is just a different standardized. I have broke the computer. Where'd that n go? That n should be 200. And right here, how many degrees of freedom? 199. You don't multiply it by that. You just solve. And we are getting 2.83. Don't tell me the p-value now. It's a very small p-value. It's like 0.000. No, 0.002? 0.005? We'll show that here in a second how we got that. What is going on? Sorry. Oh, I hit that play and rewind and it brought up player on my computer. Question in the back? I saw one.
Why is it not negative?
Oh no! Why is it not negative? Great. Wait. Yes, it should be, right? Let me just think. We hypothesize 87 is true. Correct. Great job, sir. Are you in my class? Dang it. I award you some extra credit. No, good catch. That's our first mistake of today that we've caught. Who knows how many other ones there were. But you are correct because we landed well below what we hypothesized, right? Does that make sense? We landed well below what we hypothesized. So the z-score should be negative. Think, if I expect 87 and I land at 85, is that below? Yep, and 85 minus 87 is negative 2, and then we're just dividing that by something. When you divide something, and the bottom can't be negative because it's like a variation thing. So we have here a negative z-score, which means we landed below what we expected. Great job, good catch. I do make mistakes every once in a while. And we can go over here, and let's hop to the t-applet, the secret one, which everyone's going to know about now. Let's hop to that t-applet. I'm on the distributions page. If you're wondering how I got here, you would go to the online resources page, go to distributions, and I'll show you, I'm not going to click it. Click distributions, but don't click any of those tabs, and then type T after where it has everything. Like you'll just type T, and maybe it's slow because of our internet or who knows what. Don't worry, there's other applets, but this is mine that I created or had a very good hand in. And so what do we put for the degrees of freedom now? 199 degrees of freedom. We go to area from a value. We go outside of 2.83, was it?
Yeah.
You know what's the good thing? Since we're doing the two-tailed test, now since this was a test, we probably would have lost some points if we said our t-score, we would have lost some points if we said the t-score was positive because it's not. But the good news is that we have to do the plus or minus because we're doing a what p-value, or a what-tailed test. Two-tailed test. So does everyone, go ahead.
T, right? Not Z.
T, correct. I accidentally said something there for a second. I said the wrong one. We're doing the T, and it's two-tailed. So we have to do the does not equals test. And if you look right here, if I had tested greater than, well, let's do it this way. If I had tested a one-tailed test less than, what would my p-value be? If I had tested a one-tailed test less than, what would my p-value be? If I had tested a one-tailed test, 0.00, because I would take this right here, which is my t, and let's go below. And these are good questions. Say it again?
That's the way to right?
Yeah. It's going to be half of that. Does that make sense? Probably if we carry out another decimal, it's going to be half. These are not pretty numbers, and let me make them pretty here real quick. I'm going to change what we got for the t-score just slightly to make it nicer, so that way it looks really good. I'm going to change this so it needs to be a little bit smaller. So let's add that in. Cool. And we'll pretend that's our t. Sorry if it's a tiny bit different. I'm going to put this to here. And then I'm going to put this positive. It might get mad at me for a half second. And then we're going to delete it. Dang it. Yay! So what is half of 0.005? Half of 0.005 is 0.0025. And you see how that is the one tail? So if you take this tail and double it to the other side, what will you get? 0.05. And there's a little decimal extra there, but it's just because of extra digits that we're carrying. But does everyone see, if you want to get the two-tailed, What do you do from the one tail to get the two tailed? You double it. Does everyone see? If you double this, you would get, and I'll leave it up the way it was, you would get the two tailed. But how about if we want the greater than test? What would be, so go ahead and try to figure out now, what would be the p-value for the greater than test? The p-value for the greater than test would be 0.9975. Is that what it says up there, 0.9975? And how did I know that? Because the p-value for the less than and the greater than do what? Does everyone see that visually here, that the less than and the greater than, you see that little area, that 0.0025, and that's 99.75%? The less than and the greater than p-values add up to 1. But then the two-tailed test is double the what p-value? The two-tailed test is double the smallest p-value. Does everyone see how this is double the smallest? Just pretend it says 0.005 for the moment. The two-tailed test is double the smaller one. The two-tailed test is double the smallest. The less than and greater than add up to 1, and the two-tailed test is double the smallest. So that is our result. Our p-value is this right here. Does everyone see the p-value? Let's go back, and we have a p-value of crashing. So p-value of 0.0051. That is our p-value. Now, what is our usual alpha? The question might say alpha equals 0.05, right? Is that less than 0.05? When the p-value is low, reject the null. Now, here's the hard part for a lot of people. They say, how do I word this? The way I do it is I try to go back here and read this as a sentence. And a lot of people do this. A lot of people write this, or no, I've seen this. I think this is the more common. Read this right here as a sentence. The null states equals 87. What equals 87? What? The null states the true mean equals 87. So the null states that the true mean score students think they'll get on their test, on average, is an 87. I reject that the true mean score students think they'll make on the test is an 87. I have evidence that the true mean score students think they'll make on the test is not equal to 87. Do you see how all I said before this, what did I say? I reject the null that the true mean score students think they'll make on the test is an 87. I have evidence for the alternative that the true mean score students think they'll make on the test is not equal to 87. So say those as a sentence, reading through it with I reject, I have evidence. But if you don't reject, what would you say? I don't reject, I don't have evidence. Does that make sense? I don't reject, I don't have evidence. I reject, I have evidence. Don't reject is the same as saying what? If you don't reject, it's the same thing as saying fail to reject. So I fail to reject, I don't have evidence. I do reject, I do have evidence. So let's come to our conclusion here. I'm going to try to write this without doing that perfect structure. I reject that the true mean score students think they will make on the test is equal to 87. I have evidence they think they will make a different score than this. I've pretty much said the same thing, right? I reject the null that the true mean score students think they'll make on the test is an 87. I have evidence for alternative that the true mean score they think they make on the test is different than 87. Well, that pretty much does this chapter. We did one earlier on in the review. Please go back and review. I'll probably try to timestamp these in the videos. But you notice I already knew before all this started that I would reject the null. How did I know that I would reject the null at the 0.05 level? How did I know? Because it's not in the confidence interval. And a 95% confidence interval is the same as a what-tailed test? Two-tailed test with 0.05 alpha. So I already knew anything outside. I could have done 86.5. Would we reject that? 86.5. We would reject it. I could have done 86. Would we reject 86? So the p-value for 86 has to be what to 0.05? Greater than. So you can type that in your calculator, like, boom, p-value for 86 is greater than 0.05 when you test it on the does not equals. So when I composed this problem right here, I took our previous problem, which is in the video, check it out if you want, on how to do a confidence interval for a single mean, and then I thought, let's use a value outside the interval, and I already know the conclusion. I already know if I do this properly, I will reject that value, because it's not inside of a 95% confidence interval, which means we reject it at the 0.05 level on a two-tailed test. And the two-tailed test is the what sign? The does not equal sign. Nice job.
You said you
Go ahead.
find the p-value on the calculator. How do you do that?
Yeah, the p, and let's review. I'll say it loudly so everyone can hear. To find the p-value on the calculator for this one, go to, and make sure to practice this if you want, go to t-test. T-test. And let's write a little calculator help section here. I'm going to review the calculator. Remember, only do this if you practice this. So go to stat test. So calculator help, and go to stat, and then test. Is it test or test? Test, right? Test. Stat test. Stat is in the middle up part of the calculator, and go to stat test. Now there are 4 things we must know about the general things we use. You can do the chi-squared test, which is really easy. We might do that if we have enough time. But the general ones we use have 4 different things. And there's help videos for each of these on the Stat 201 channel. So I've got a TI help section. But the first thing we have to ask ourselves is, question 1, how many samples? And the answers are 1, which is default, and 2. So the answers are 1 and 2. The next question we have to ask ourselves is mean or proportion? So we have to ask ourselves if it's for means or for proportions, and the default is means. The third question we have to ask ourselves, and it'll be easier when you see it if you're looking at your calculator, T or Z, there's no default there. And the last thing we ask ourselves is test or interval. Let's build what we should look at. What do you think we just did? What statistic did I use to do this test? I used a T. Wait, and I just said it. What statistic did I use to do this? I did a test, right? So that sounds like t-test, right? But we'd probably say, looking at all this, it'd be a 1 mean t-test, right? 1 mean t-test. So with this in mind, you might look for something like 1 mean t-test. But what do you actually need to click? You actually just need to click t-test. Because if it doesn't have a number in front of it, what's the default? It's what? No, wait, if it doesn't have a number. If it doesn't have a number, the default for the number is 1. If it doesn't say means or proportions, the default for that is mean. So when it says t-test, that's for 1 sample for the mean, and using the t-statistic, doing a test. Don't use z-test because you won't see the same notation. So when you click t-test right there, do you see the same notation that we put? Oh, did I lose my spot? Oh, no, we need to move this below because that's out of order now. Because when I make this video, I'll have people, you can click through here. So when you look at what you have in the notation, do you see notation just like this? Now you might not see y bar, you might see x bar. So y bar is the sample mean of variable y, x bar is just the sample mean of variable x, same thing, just calling it y or just calling it x. So we have s, and your calculator calls it s sub x, which is standard deviation of variable x, all that good stuff right there. Does that make sense? So I've got videos for each of these, and feel free to email me if you're like, Brian, which chapter is what? Do you guys want to do maybe chi-squared now? Let's do some chi-squared. We just did that a while ago. And let's do this by hand right here. Okay, chi-squared is one of my favorites. We haven't done 2 sample mean. Maybe we'll come back to that. So let's do chi-squared. You know what? Actually, let's do this. I'm going to do a different thing. I'm I'm going to do jump output because we're running low on time, and I really want us to look at some jump output. Do you guys want that? I think that'd be very valuable if you know how to read all the jump output I can make to show you what each thing means. Would you guys like that? Because we definitely put jump output on these tests. So let's pull open jump right here and get some jump output. And, oh no, that's the one I don't have a license for still. Where is it going to open? So you're like, you do not have a license. We'll see how my computer does with running jump. All right, let's go here and go jump pro 14. Jump pro 14. All right. Where does it open? Up. Because I want us to do 2 sample means, so this should open a half second here. How's my onliner doing? We have 1 onliner. I was like, man, we're gonna have like 50 people watching online. I hope this gets used a lot over the weekend. I hope people are, because we're really going through a lot of the topics. Do you guys feel like you understand a little bit better? It really takes sometimes, I mean, we're basically just reteaching it. This is like the Cliff Notes versions. I can't promise I covered every little detail, but I would say I've covered like 50-60% of the test material so far. Like just in 2-3 hours of doing stuff, we've covered a lot of test material. And hopefully I didn't blow up my computer right now. The video is completely frozen. Maybe opening jump was a bad idea. Up. Where's jump? Is it over? Let's jump over here. Oh, let me do this. Okay, 2 seconds. We will be looking at jump. Not 2, but maybe like 10 seconds. Okay. Let's take this and bring this. Is that not where it's at? Whoa, whoa, whoa. Go over here. How do I open jump on that screen? Oh, wait. I want to go to jump. Oh, no. Dang it. I need to take that off my taskbar. I still have jump 13. Sorry. Jump pro, wait, project data version. Open. This is the problem with dual screening. Is it over here? Maybe I won't be able to do jump on this. How do I bring something over to my other screen? Is that not the way? Oh, that's... All right, I think I figured it out. Got it. All right, here we are. Here's our survey data. Let's go ahead and do this right here, and you should know what output you're looking at. Okay, can you guys tell me? Oh, is it wow. It opens up on my other screen. Can you guys tell me, ignore conditions for a moment, but can you tell me what output you're looking at what output are you looking at right here? What kind of hint? Confidence interval for what? For, I see a confidence interval, I see all this. What chapter do you think this relates to? Hint. Do what?
Quantitative, chapter 17.
Correct. One sample mean. Does that make sense? Because if you look, I'm analyzing one variable. I'm analyzing weekly hours worked for one group. Does that make sense? And here, I'm going to bring the online chat back. So I'm analyzing one variable, one mean. And then let's go here, and let's go to test mean, and let's test the value of 7. When I test 7, do you think I'll reject 7? Why? 7's in this interval. Do you see that? I can actually tell you, I'm going to change this to 7.04, and then I'm going to tell you the t-statistic. The t-statistic for this. The t-statistic for this is going to be about, let me change it real small here. Sure, we'll keep it to that. And then we'll put this in. The t-statistic for this is going to be very close to 1. It's going to be about 0.99. Am I right? 0.99, negative 0.99, sorry, negative 0.99. I'm flipping the negatives in my head these days. But I was really close. I should have just said negative, right? Look at what I did, though. The standard error, what is the formula for this? Standard error is what? S over square root of n. And then all we do is we take, if you notice all I was doing in my head was adding these numbers. Well, actually, we are one standard error below. Does everyone see the difference between the hypothesized? What is the hypothesized value here in notation? That is mu naught. What is the actual estimate in notation? Here, it's right there also. It's a statistic. It's a mean. It's a sample mean. Does that make sense? The degrees of freedom, why are they 1307? Sample size right there. And the standard deviation is 11. What do you think 11 over the square root of 1308 is? 11 over the square root of 1308 is probably 0.3. If you have 6.7 and you go up 0.3 and 0.3 again, how many times have you gone up 0.3? 2. And you'd get 7.3, right? Do you see this 95% confidence interval? It's basically 2 standard errors. Does that make sense? Because we say usually a t of 2 for larger sample sizes is a 95% confidence interval. So if you were to read this, you would say, I am 95% confident the true weekly hours a week students' work is contained in the interval 6.14 hours to 7.34 hours. Now, this is a very skewed distribution, but our sample size is very large. If you notice, we're actually covering every single topic right now, right? But you should know what all of this output means. Can you pretty much identify? If we tested the two-tailed test, where would the p-value be? Which p-value is it? 0.32 basically, right? And think we got a z-score of -1. What is inside of -1 and 1? Basically on a z-score? Inside of -1 and 1 on a z-table is basically what? Your first number on the empirical rule. 68. And what's outside? 32. And that's why that answer looks like that. Does that make sense? Because I made the t-statistic basically -1. And since the sample size is very large, it's basically a z-score. And that's more advanced stuff like the t turns into the z. But since it's basically a z-score, I can just talk about it like it's a z-score now. Not really, but kind of use it that way. Does that make sense? Let's look at comparing males and females and how much they work. So 2 seconds, I'm going to have to, let's go here. Let's do born in Tennessee. Oh, that'll be interesting. We're going to do born in Tennessee and how much people work. So born in Tennessee, and then how much you work. Where's weekly hours work? So do people work more? We're going to try to answer this question like it's a test question and use the output. Do people who were born in Tennessee work more than those who were not born in Tennessee? Take a second before I show this here and write the null and alternative. So we're testing how many means here? 2 means. We're going to do a review of 2 means by showing some output here. So we're testing 2 means. Do people who were born in Tennessee work more than people who were not born in Tennessee? So how do we write that one? I'm going to have to hop back to here, and we need to write a null and alternative again. And our null and alternative, let's grab the null and alternative. Let's go to here. And we need to write, let's do born in Tennessee, not born in Tennessee. I'm going to cheat and look at the output because the output's going to do it a certain way. And I can't remember how the questions are written. So, output appears on this screen. Okay, let's bring the output over. And I'm using the output to tell me how to write it. And the answer is going to be yes minus no. Okay. So when I write this right here, it's going to be mu subscript yes minus what? Mu subscript no. And what will we say that the difference between these two is equal to? We'll say that the difference between them is equal to 0. And we've just done the null and alternative for the next chapter. Now, I want to see if people who were born in Tennessee work more. Does that make sense? So we want to see if people who were born in Tennessee work more. Well, then if this number is bigger, the difference would be what? The difference would be positive, so we're looking for the alternative greater than. You can also check it because the greater than sign, if you put it here, which technically you could, would be there. Does that make sense? That the yes group is bigger than the no group? And one thing I want to point out, if you have the jump output, all you need to do with your jump output, when you see this, here's the trick. You guys ready for the trick? Right before this, guess what I would write right here? I wish I could write on the screen. I would write mu yes minus mu no equals 0. When you see this output, you can do that. Does that make sense? Mu yes minus mu no equals 0. Let's try another one here just to see how quickly you can do the null and alternative and just use that trick I just showed you. Let's do, we can't do too many of these because there's so many answers. We're trying to look for a two-sided one. Well, why not? Let's do if someone has student loans and the number of languages they speak. So it's basically going to look the same, and see if you can write the null and alternative using the trick we just did. It's going to look the same because it's yes, no. So what would be, what would you write right here before this? You'd write mu yes minus mu no equals 0. And then depending on which sign, like does not equals, greater than, less than. And if you notice, this is what we've done right here. Mu yes minus mu no. Whatever the names of the two groups are will go right here. Does that make sense? Like on your practice test, it's got USA and Britain. So if it's USA minus Britain, you would just write what? If it says USA minus Britain, you'd write mu USA minus mu Britain equals 0 would be the null. So this is what we want to do right here. We want to know how to write that null and alternative when we see this output. Now, what does this difference value right here mean? And I like our results. It was the difference. So which group was higher? Which group works more? Yes group. Does everyone see the difference is positive? So that means the yes group worked 0.69 more hours on average. The standard error of the difference is from the formula square root s sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2. But when you think about this, this is one of my favorite things about this output. Everything we've been saying today is when we do a test, we take a difference and we what it. Do you notice how those two numbers are kind of equal? So if you were to put a divide sign right here between them, you'd basically get something close to 1. Does that make sense? And you know what? With something close to 1, those p-values, I'm probably going to have a good guess on them again, right? Question?
Is it always going to be equal to 0?
Yes, for our class, yes. It's so funny, someone once told me, they're like, I didn't know you could change it. Like, yeah, you can test any value you want. But usually we just test to see if the difference is 0. You could test, imagine you work for a company where they say, we want to know that moving the machines, like, you have pill machines that dispense pills, right? So we want to say if we put the machines on this side of the hospital because it's going to cost time, money, and all these other things, it's going to save at least 2 minutes. So the average amount of time with the current way minus the average amount of time with the new way, the difference should be more than 2 minutes. Like, do we have evidence that there's at least 2 minutes saved? So you could test 2, and then that would just be the value you would test against. So, and we won't do that in our class, though, so don't worry. But good question. I like it. And so right here, it's funny. Someone told me that. They're like, I never know you could test a value that wasn't. And I was like, yeah, you can.
Hey, chi-squared is always independent of O.
Oh, that's going to be interesting. Something tells me we're not online anymore. That's scary, isn't it?
Yeah, that happened at Stoke. The lights just went off and turned back on, but these lights aren't turning on.
Yeah. Okay. Is my computer? Oh no! You know what's really bad? Oh no! My computer right now is on battery power, and the fan like literally turned on because I'm running so many things that my computer right now is like, it's having to do all of it without charging, and my computer's like, no. Hey, we're still broadcasting, I think. But guess we'll wait a minute. What'd you do? Valapalooza, everybody. That's going to be really interesting to see in the video.
The lights go out. So I guess that's the end of the.
Oh, man, I really want us to do more jump output. because I really wanted to do the chi-squared stuff. If you guys want to wait a minute or two more, I'll wait a minute or two more, but it looks like I'll probably be logging offline because
So it's still live right now?
we are still live.
The power is out, like, all over.
All over campus?
Yeah, someone just put more grouping for our floor, with the power out.
Is it because people are doing all booths or just out?
Let me cancel. So everybody who we're broadcasting to online, we are leaving.